Welcome to The Explainer. Today, we're diving right past the pop culture myths to systematically deconstruct the actual mechanical breakthroughs and philosophical evolution of Albert Einstein. We're looking well beyond the wild hair and those famous equations to really understand the precise architectural shifts in his physics.
So let's start with a pretty provocative question. Back in 1944, a young philosopher of science named Robert Thornton wrote to Einstein, asking for advice on teaching physics. And Einstein's reply? Well, it gives us the absolute key to understanding exactly how his mind worked. He basically admitted to being an epistemological opportunist, meaning he totally refused to be tied down to just one rigid system of philosophy when analyzing the physical world. That adaptability, that was his secret weapon. Here's our roadmap for this explainer. We'll be looking at 1. The philosophy of physics, 2. The miraculous year, 3. Special relativity, 4. General relativity, and finally, 5. The quest for unification. Part 1. The philosophy of physics. Let's look at his unique approach. In a 1919 article in the Times of London, Einstein formally divided physical theories into two distinct types, constructive and principal. Now, constructive theories are your bottom-up models. They try to build complex phenomena out of simple hypothetical building blocks, like kinetic theory modeling gases as bouncing particles. But Einstein felt these premature constructive models often got in the way because there were just too many unknown variables. So instead, he relied heavily on principal theories. These are top-down. They start with highly confirmed empirical generalizations, think of the laws of thermodynamics, and demand that all other physics simply conform to them. He used these principal theories to build the absolute bedrock foundation of relativity. Section 2. The Miraculous Year, his Annus Mirabilis. Let's dig into those 1905 breakthroughs. This timeline plots an absolutely incredible sequence of discoveries. And what's really fascinating here is that many of his epical contributions during this phase actually stemmed from his intense focus on just one single problem, analyzing the fluctuations of a delicately suspended mirror inside a radiation cavity. That one single thread literally led him to redefine the nature of light in March, the statistical mechanics of random fluctuations in May, the electrodynamics of moving bodies in June, and mass energy equivalence in September. Just a staggering output. Take his work on Brownian motion from May of that year, for example. At the time, physicists knew they couldn't just measure the mean velocity of a microscopic particle suspended in fluid. It was way too erratic. So Einstein sidesteps this entirely. He focuses on the particle's displacement over time instead of its velocity. He showed that this random walk was a form of diffusion, proving that the mean displacement is proportional to the square root of time. And by doing this, he mathematically nailed down the Avogadro constant. This wasn't just some neat math trick. This strikingly visual mathematical proof absolutely guaranteed to a highly skeptical scientific community that atoms and molecules were in fact physically real. Number 3, special relativity, deriving the mass. Without making any assumptions about the constitution of matter or intermolecular forces, Einstein used a brutally efficient logical progression. First, he completely tossed out the concept of the luminiferous ether, transitioning physics over to a foundation of observational and formal symmetries. Second, rather than jumping straight to postulating the invariance of the speed of light across all frames, he just postulated its constancy in a single resting frame. And from there, he used remarkably elementary algebra and differential analysis to derive the famous Lorentz transformations. It was just an absolute masterpiece of logical economy. And this purely kinematic work in June led him to a profound conclusion by September of 1905. He realized that a body radiating energy must lose mass. That led directly to the statement, the mass of a body is a measure of its energy content. Which brings us to what is perhaps the most famous mathematical statement in history. But here's a really surprising fact. The familiar E equals mc squared isn't exactly how Einstein first wrote it down in his 1912 manuscript. He actually originally used an L to represent energy and a V to represent the speed of light. It was only later standardized to ENC, with C coming from the Latin celer, meaning fast. He even suggested testing this radical new equation using salts of radium, predicting a mass defect that would, as we know, later unlock the entire era of nuclear energy. Part 4. General Relativity. The engineering of gravity. Looking at this primary text, this is the preface to his 1916 publication summarizing the theory, we get this really raw glimpse into his methodology. Einstein explicitly notes that he treated the empirical physical foundations of the theory in a, quote, stepmotherly fashion. Instead, he adhered to the physicist Ludwig Boltzmann's precept on mathematical elegance. He was totally driven by formal perfection and geometric necessity, not just by trying to fit equations to observational data. To engineer this theory, Einstein started with what he called the happiest thought of his life, the strict equivalence of inertial and gravitational mass. He realized that if gravity and acceleration are indistinguishable, well then gravity isn't a traditional pulling force at all. It's actually a curvature of a four-dimensional space-time manifold. Massive objects are simply following the shortest possible paths, or geodesics, through this curved space. But to express this mathematically, he needed some serious help. So he collaborated with his former classmate Marcel Grossmann, who introduced him to the absolute differential geometry of Ricci and Levi-Civita, which Einstein ended up renaming tensor analysis.
By 1915, this quest put Einstein in an insanely intense race with the preeminent mathematician David Hilbert to finalize these gravitational field equations. Hilbert actually submitted a paper with the correct equations just days before Einstein's final presentation, though to his credit, Hilbert gracefully acknowledged that the physical theory belonged entirely to Einstein. Today, that foundational mathematical formulation is still known as the Einstein-Hilbert Action.
And despite his self-described stepmotherly treatment of the empirical data, the math was staggeringly correct. The new field equations immediately solved the anomalous precession of the perihelion of Mercury, which was a massive problem that Newtonian physics just couldn't crack. It also perfectly predicted that massive bodies would bend starlight, what we call gravitational lensing, and that gravity would actually stretch the wavelength of light, known as gravitational redshift.
Finally, Part 5, The Quest for Unification, the final chapter.
For the last 30 years of his life, Einstein tried desperately to weave together gravity and electromagnetism into one unified field theory. He explored some incredibly dense mathematical frameworks. He looked at Kaluza's five-dimensional theory. He experimented with teleparallelism or Fern parallelism, trying to maintain a concept of distant parallelism inside a curved space. He became totally obsessed with the geometrization of the electron field, attempting to derive the field equations by varying 16 specific directional variables, which were known as beam quantities. Ultimately, though, this highly complex approach was viewed by some, including his old rival Hilbert, as a, quote, colossal detour. By constantly varying these mathematical structures, Einstein consistently arrived at an overdetermined system of differential equations. Despite literally decades of intense mathematical labor, the equations continually failed to produce the one thing he demanded of them, a singularity-free model of the electron. The mathematical architecture was just simply too constrained.
So, we'll leave you with this to consider. Einstein spent the first half of his career revolutionizing physics by relying on top-down principle theories, only to spend his later decades trapped in a dizzying search for a bottom-up geometric construction that never actually materialized. How did one man's philosophical shift from practical principles to an unfinished dream of total unification shape the absolute limits of how we understand the universe today? Think about that the next time you look up at the stars.